Professor Juliane Simmchen from TU Dresden. She just moved to Strathclyde. And she's going to talk about biomimetic behaviors of active matter. Thank you so much, Juliane.
Oh. Thank you, Danilo, for the kind introduction. And as just mentioned, we are actually located in where? Okay, we're located in two sites. So most of the work that you're going to see today is being done in Dresden, but we have actually recently moved to Scotland. And Scotland, as everybody knows, is a very good place to study soft matter. We have pretty much of it. And the Scottish people also do quite some interesting things out of their traditional soft matter, even though if you would eat it, it's probably baked. If you're curious what we're doing with this, just look at our recent publication. And another small detail is that our new lab is actually located in the Thomas Graham building. For those who've not heard the name, he's considered the father of colloidal chemistry, which I find quite exciting, very inspiring building to work in. Good. But what we're talking about today is active matter, as several talks this morning and actually for the rest of the meeting have been talking about. So I don't really need to spend much time of an introduction. Much of active matter is actually biological, so from these like nice flock of birds to also the microscale organisms. But what my group is concerned about is mainly artificial active matter. We believe that we have more control if we don't have like the biological fuzziness in the equations. So what we do is we make our own particles and we modify them in a way that they can self-propel. Andres has given a nice introduction to Janus particles. This is how we actually make them, right? So we take inert particles. We work most of the time with just silicon dioxide. We put them in a monolayer, and then we evaporate a thin layer of a catalyst on top. And then when we put these particles into some kind of fuel, some kind of a reaction, most of the time catalytic, happens on the catalyst half, so that we get more product molecules there, which then leads to self-propulsion. So you'll see these particles, there's no bubbles or anything, they just move, and they take this quite interesting half and half orientation. What you see here is silicon dioxide covered with platinum, and you see they move towards the inert side, sort of white side, which is silicon dioxide.
Is this real time?
This is real time, yeah. So these kind of systems, they have been around for quite a while, about 20 years now. So you wouldn't be able to publish just this. So what we usually do is we create kind of interesting environments for these particles and then see what are their responses. And most of the time, this is really bio-inspired, because this is exactly what you would expect a microorganism, so bacterium or an algae or something like this to do. If you look at biological responses, they're very often described by this word, which comes from Greek language. I don't think we have any Greek people in the audience. And it means agreed on motion. You might be very familiar with this word, just from like the taxi, where you agree with the driver, and then he hopefully brings you exactly where you want to go. And this concept, this word, is used in biology to describe a lot of different concepts where a determines the direction or the motion. So this is what we're going to talk about, several of these phenomena. And let's start with a very simple one, which is gravitaxis, so the response to gravity. You all know on this planet we can't really get rid of it. So we just see what is the actual effect of it. And just because we live in this real world, we have to all the time cope with gravity. And our particles, they're simply density mismatched, right? So their density is higher than the surrounding water and also higher compared to the surrounding hydrogen peroxide medium. So what they usually do is they kind of sink to the bottom. For the normal platinum-covered Janus particles, this has been studied. So because we are on Earth and we can't really just get rid of gravity, what we do is we just take our microscope, we incline it. Usually the students get a bit of a heart attack. They're very scared of like inclining a very expensive microscope. But then you get quite interesting observations. And as I said, this has been observed before. The platinum particles, when they are in this kind of an inclined plane, they do move upwards. Why is that? Just because of gravity. The platinum density is about 10 times higher than the silica density. So the platinum part would orient upwards. And then because they move towards the inert part, this leads to an upwards motion. But what if we actually just change our system? So one particular system that my group is working quite a bit with in the latest times is a very similar geometry. So we still work on Janus particles, so half inert, half active. But now we actually change the catalyst from platinum to copper. Copper also catalyzes the degradation of hydrogen peroxide to just water and oxygen. But when it actually does this, the hydrogen peroxide also oxidizes the outermost surface of the copper to copper oxide. And this frees a few positively charged copper ions. So the overall potential that you'd measure in a zetasizer of these particles is much less negative and closer to zero, slightly positive. When we put these particles into fuel, we still have more product molecules on the copper side, and this leads to motion. However, when we look at this video, now you see that the particles move actually to the opposite direction. So instead of moving towards the inert side, now the particles move towards the catalytic half. So if we put exactly these same particles into our gravitaxis setup, because this has still a higher density than the inert part, the copper part would still be, so this is just the comparison experiment. If we don't incline the microscope, the copper part would be still oriented downward, but because now the particles move to the other direction, this leads basically to the opposite phenomenon. However, we can also create much more sophisticated and complex environments. And the next one that we would actually like to look at is rheotaxis. This is again very bio-inspired, and I think it's quite safe to claim that without rheotaxis, none of you would be here. And this is because one of the most well-known systems to actually perform rheotaxis are sperm cells. So you see this if a flow is applied in this direction, the sperm cells, they use this as kind of a guiding mechanism so they move up towards the oocyte, and there's like naturally like a flow. So the sperm cells use this as like a guidance mechanism. If you look at this, how does this work? This is very similar to what you see with the weather vane in your garden, that because you have this completely asymmetric structure, you have different interactions on the different parts of the sperm. So it's generally was generally concerned or believed that this kind of very asymmetric weather vane mechanism is necessary. So, but we still wanted to see, even though we don't have this kind of asymmetry, maybe if our Janus particles were able to do this kind of a rheotaxis. So we created this kind of a little setup. We used like a square capillary where we can apply an external flow. And then we put the particles in the middle and started applying an external flow. This is a view of the microscope. And if we don't apply an external flow, the particles go completely randomly in all kind of distributions. So the probabilities of finding them in any random angle is completely equal. However, if we start to apply an external flow, you see that the particles orient and they actually start crossing the flow, so that when we measure their angles, we do get very, very pronounced peaks here at 90 and minus 90 degrees. So basically moving upwards, or like, so you have to think about this as in a microscope, so it's not upwards, it's just like in y direction, in this direction, in this direction. We were quite disappointed because we actually wanted to see rheotaxis, but back then we termed it cross-stream migration, and yeah, just went with it. It's nature, so you can't really do anything about it. A few years later, when we had actually discovered the copper Janus particles, we're like, oh, let's go back to these old experiments and let's actually see what happens when we put this new system into the flow. So we did this, and here you already see the flow applied. You have to believe me that these particles also move in random directions if there's no flow. You see here 2 little tracer particles. They are just silica, just so that we can see the flow. And you see that the active particles, they're actually quite sturdy, and they do manage to rheotax. So they do manage to go against the flow. So at this point, we reconnected with our friend Will Usbel, who's now in Hawaii, and he looked at some phase plots, and he finds that the actual swimming configurations that these particles are in has a stable point here, around this 90 degrees, which is upwards motion. So good, we found rheotaxis, and we can actually also theoretically explain that all of these effects that are like hydrodynamics, the chemical fields, second order effects, they lead to this like rheotacting configuration. However, when Will deviated a little bit from these very low flow rates, then he found a much more complex scenario. So there's no real way that I can talk you through this phase plot, because it doesn't have any stable point. Everything is all the time basically in motion. So what we did is we went back to the experiment and increased the flow rate. So you see it's about 5 times higher here. And now you see our tracer particles are just white, they're much faster. You see some particles are still sturdy and trying to move upwards, but most of them do actually this very interesting kind of jumping mechanism, which we found quite fascinating. And when we look at this behavior, we can characterize it a little bit more. So we see that if the particles are really close to the bottom substrate in the configuration where we can see them well in focus, they are actually aligned and try to rheotax. But then every now and then, because they have a shear flow, right? So the flow at their upper end is slightly higher than close to the bottom. The shear flow drags them away, takes them up, and then they do this kind of quite interesting, almost sinusoidal dynamics there. And then gravity takes over, they manage to reorient. They really reorient in the right rheotacting behavior for a minute or for a second, and then they get dragged away again. So that we can really put up this kind of nice plot here, where depending on the velocity, we have either rheotacting behavior, so you see this is the flow behavior, the particles get slower because they have to swim against the flow, and then at higher flow rates, we see this kind of jumping behavior here, which we thought was quite interesting. I'm not aware that there's any biological analogy for it, at least. Haven't come across any. Good, but that's not the only cue that nature uses, or that nature superposes to microorganisms. And one that you all have experienced yourself is chemotaxis, so the motion towards or away from a chemical stimulus. And there are not so many experimentalists, but experimentalists hate chemotaxis because it's really, really complex to establish a nice gradient that is sufficiently stable for the Janus particles. So that was far too quick. So a few years ago, after lots of failed experiments like the butterfly setups and others, we had a PhD student together with this company in Paris, Elvaflow, and she designed this very nice feedback loop setup where we can basically establish a gradient and then stop it and counterbalance the flow so that we really have a stable gradient, which we can also characterize. So we can see this here. We did this with fluorescein so that we can actually see the intensity, and we can also calculate how the gradient stiffness evolves over time. So when we put our particles, in this case, we took first the copper particles in this gradient. So you see that the copper particles, if there's no gradient applied, they have a completely random orientation, no preference. But when we put them into a hydrogen peroxide gradient, we see that the dynamics really change strongly. So we get a quite pronounced preference here at towards the higher concentration of hydrogen peroxide, but we also get a slight peak here towards the lower concentration of hydrogen peroxide. So now you might be asking, okay, why do we get both? And we can see this quite nicely from actual COMSOL simulations. So when you look at these, when the particles are oriented correctly, let's say, then we have the same amount of activity on the two sides of the cap, so that if the particle happens to be in this orientation, it will just continue swimming towards the higher orientation, towards the higher concentration. If the particle happens to be exactly oppositely aligned, then we have the same scenario here. And as long as Brownian motion doesn't kick in and reorient the particle, then the particle would just continue swimming towards the lower gradient or the lower peroxide concentration. However, in the moment where the particle either happens to be misaligned or Brownian motion kicks in and reorients it, then the particle experiences something like this, that you have more forces and torques created in this very thin layer around the particle on one side, less on the other. So the particle will actually experience this torque, reorient, and swim towards this direction. If it's completely oppositely oriented, the same thing will happen, but the particle will not swim towards this position, but it will also orient towards the upwards position, so that we have, I'm losing the microphone, so that we have more probability to end up in this orientation. So this is quite curious, and we thought, okay, if we get these like interesting results with copper, let's try with our normal platinum Janus particles. And the Janus particles, like the normal ones, you see it here in the video, they have a very strong preference to move away from their fuel. Why is that? There's no hand-waving easy explanation for it. There's a nice model by Michael Popescu, which basically describes that Janus particles, depending on the sum of their phoretic mobilities and the difference on their phoretic mobilities, they have different tendencies to swim towards and away from their cap, and they have different tendencies to turn, so we get different chemotactic behaviors. Now, unfortunately, this concept of phoretic mobility is not something that is very, very defined. It's not something that we can easily measure in an experiment, because there is no such device, there's no setup that really allows us to easily measure this. One thing that we can kind of heuristically define is these mobilities, phoretic mobilities. They're probably also somehow depending on the interaction of the solutes with the surface of the particle. And when we try to influence these, one way that seemed rather intuitive for us is actually to change the surface charge of the particles. So my PhD student Suyao actually did this. So he took a normal silica surface, a normal silica particle. Silica generally has a negative zeta potential. If you add platinum, this part of these like negative charges get covered, so you get to slightly less negative values, but you end up with, for the whole zeta potential of a Janus particle with around -30. So what Suyao did is he took the silica part of the particle, he applied APTES, which is a silane with an amino group at the end. So this amino group really likes to be protonated, so frequently induces a positive charge. When we do this, cover the whole thing again with platinum, and then measure the zeta potential, we get to slightly positive values, around +5. And then we look at these particles, and we see, so when we characterize the motion, we see that our normal silica Janus particles, they move towards the inert part. When we look at the ones that we just created by functionalizing them, they move actually away from the inert part. So very similar to what we've observed with the copper particles, where through like the catalytic oxidation of the copper, we had also been creating a slightly positive particle charge. The dependence on the hydrogen peroxide concentration is just very similar. So, Suyao also looked at basically why do we get this inversion, and because the phoretic mobility is not really defined, we can't quite say, but depending on whether Suyao uses like a diffusive phoretic model without any charges or includes charges into the simulation, we basically get the swimming direction inversion in both cases. Good. So now some more interesting experiments. What happens if we actually look at their chemotactic behavior? So we've seen before the normal Janus particles, when we put them into chemotaxis, we see they move away from the high concentration fuel. I've seen this video too. And we see when we take the positively charged Janus particles, they move towards the higher concentration. So opposite behavior. Very nice, reliable behavior, very nice Rose plot. So we see that by tuning the surface properties, we can quite nicely actually tune the motility response of these particles. And then it was the easiest exercise to put these particles also in the rheotaxis setup. The negatively charged particles, they just do cross-stream migration, as we had already previously observed. But when we put the positive particles, they do perform rheotaxis very similar to what the copper particles would do. And if we increase the flow speed, we also see the jumping behavior. So all of these behaviors are even robust comparing like different of these swimming systems. So that was quite a nice surprise, or quite a nice observation for us, that by tuning the surface properties, we can actually tune the response to the environment. But so many of you are actually interested in collective interactions. So we want to observe not just like one particle, but like ideally many. But if you look at this video, and here I'm cheating, these are not our normal particles, these are photocatalytic particles, because we need, so our particles are just a source. These are a source and a sink, so that they can interact well. They need to have these properties to have a source and a sink, so basically some electrophoretic contribution. You see, this is quite messy, right? And in order to understand this well, we started to look at actual pair interactions. If we think about like these particles, why is that not moving on? Okay. Then even if you have a defined number, the interactions are quite tricky to characterize. You know, they can like go in all kind of directions. So we use a little trick here. We use this kind of a groove. So we made substrates that had these like little imperfections, and these imperfections confine the particles. So when we put our particles into a groove, they don't escape. So we basically created like a one-dimensional system so that we can study the systems a little bit better. These are the normal platinum particles, quite uneventful. They go towards each other. They don't really notice each other until they come in proper contact. But then once they found each other, they just keep pushing each other. They have roughly the same propulsion. So they are basically just stuck in that system. Sometimes they escape, but most of the time they're really just stuck there and stay there. So then we asked our collaborator Amin to put up a little model, and into this model we fed the data that we could extract from experiments, and the data that we gave them were basically particle distances and the angles of the individual particles. Then you can probably imagine we repeated the same thing with the copper particles. Now pay attention, this is cool. So you see that they actually can take note of each other at much larger distances. I'm going to try to go back. This video is really cool. You haven't seen it. So there's a few particle radii in between when they take note of each other, and then because they're confined in this little groove, they just flip around and move back. If we again look at the trajectories, at the distances, then we can really see this. In the theory prediction, we don't quite see that the particles have this distance between them, but they still come a little bit closer. However, when we now take away the grooves and we let the particles swim freely, we see all kind of different trajectories depending on the initial orientation of these particles. And what is quite nice that Ramin and his team, they could actually always find trajectories that really match well what we observe. It's not quite deterministic, so we can't say at this angle exactly this trajectory comes in, because there are many degrees of freedom, but you can always find trajectories that match the behavior really well. Okay, with this, we are like on the way to characterizing larger particle systems, and for me this brings me to the summary. Yes, so I showed you that there are quite some interesting biomimetic effects. For example, response to gravity, and we can dramatically change and modify them just by changing small details of the particles, which can be either the catalyst but also the charge of the inert part. I showed you that we have cool responses to flow, to chemotaxis, and we have quite interesting pair interactions where I believe we have to study individual interactions first before we can actually go to really larger systems to truly understand what we see there. Good. Just show you the people who've done the work. Most of the work that I showed you today was done by Tsu Yao and Priyanka. Priyanka is now in the MP in Mainz. These are the people who are currently working in Dresden, and these are the people who are currently working in Scotland. And with that, thank you very much for your kind attention.
Very interesting. Questions for you, Juliane? Oh.
Okay, thank you for your talk. It's very interesting. I was wondering, I saw that in your videos, you always put like the oxygen peroxide concentration that you use to make the active particles self-propel. Is it a critical, how much oxygen peroxide you have, or it's just some fixed concentration to see this behavior?
This depends very much on the system. So, for example, for these catalytic Janus particles, you need at least 0.5% of hydrogen peroxide. However, we do have other systems. The one that I showed you in the collective video, these are titanium dioxide gold particles, and they swim at very low concentrations, about 0.05%. But now we also have like rod-like systems that swim in even much lower concentrations. So it depends very much on which material you're using.
I see. Thank you.
Thank you for the presentation. Have you tried or have you considered to produce particles with a density closer to water and smaller particles too?
So you cannot so you cannot produce particles that have a density matched to water. What you can do is use polystyrene. Polystyrene has a density of like 1.1, which is close to the density of hydrogen peroxide. However, if you put a cover of any kind of catalyst, this has a density that is like 8 times higher in case of copper, 20 times higher in case of platinum. So I was never really interested in it, but so when we discovered this density match between polystyrene and hydrogen peroxide, Ivo Buttinoni, he took this idea on and they studied it. However, they didn't quite, so they found some interesting dynamics, but they didn't quite get to the density mismatch system because they rely on the catalyst still.
Yeah. And about the size, because you're working with 1 micrometer size particles?
Yeah, I mean, if you go to smaller sizes, you will struggle with Brownian motion. So if you go to sizes that are smaller than roughly 800 nanometers, first you have the problem that you will stop seeing the particles at some point, so you can't use optical microscopy to do the experiments. You can do DLS and things, but they don't produce nice videos, so you cannot do the studies that I've showed you in like more complex environment, because yeah, and you only get just enhanced Brownian, enhanced diffusion. Yeah, and we are just more interested in these like generating environments, looking at the behaviors. So yeah, we barely work with smaller systems.
Okay, thank you.
In the 1D dynamics video with the negatively charged colloids, it looked like there was a third colloid that saw there was a traffic jam up ahead and decided to take a detour. Was that coincidence, or is there some physics there?
No, that was coincidence.
Oh, too bad. So then the second question is, can you combine the positively charged and negatively charged colloids in the same simulation experiment?
Yeah, and Ramin was really, really excited about that, so he really wanted us to try that, so we tried it and nothing interesting came out, so they just don't like each other very much.
Okay. Yes, I'm here. Thank you very much. Very beautiful talk. I had 2 questions. One related, I sort of remember a work by Ivo Buttinoni from 2023 where he studied catalytic colloids, and he observes a sort, I don't know whether it's the same jumping behavior, so colloids were sedimenting and sort of levitating in an oscillating way. Is it similar to what you mentioned as jumping, or is it different?
I don't quite remember that paper, so I can't tell you, but I can look it up and tell you.
Yeah, we can discuss it later. And then I had a quick question about the last part of your talk, this groove. It reminds me, it's like having some sort of an optical tweezer to sort of, I mean, what
no,
people...
it's much simpler. I mean, it's much literally simpler. Just a little
Yeah. But
wedge.
the idea is, it's a, let's say, to measure interactions is what people do with colloidal systems. The problem is that here interactions might be anisotropic, and your groove does not allow particles to rotate. So you are missing the angular dependence of your interactions, at least from what I saw in here. I mean, when particles facing head to head, they never rotate. Were they rotating?
So, I mean, we do see that the measurements for the platinum systems doesn't go backwards. Okay, that these look very, very similar, irrespective of like which particle pair. So we have, I don't know, 25 of these incidences, and the dynamics look very, very similar. However, if you look at this video again, you see that
they rotate, exactly.
They rotate, and one rotates a little bit more out of plane, like a flip, and the other one rotates a little bit more.
Yeah,
so
that's why a one-dimensional model will miss this. Yeah, because the rotation is out of plane. So a 1D model, Golestanius model, might not capture this because the model is 1D, but the rotation is in the 3rd dimension.
And we believe that this rotation is also a bit of serendipity, so it really depends on the surroundings, the Brownian motion that affects the particle in that very moment. So,
and then maybe
it will be difficult to capture it.
Interactions might be not just 2 bodies, so maybe adding then higher order interactions might, okay, thank you.
Can you tell us a bit more about the model? So what is exactly being modeled? So are you modeling the hydrodynamics, the diffusion of...
Yeah, they did add hydrodynamics and spherical interactions, so rather simple. And what they did is they approximated the phoretic mobility by the zeta potential of the particles. And there was little more that actually went into the model.
This is a kind of related question. How much hydrodynamic coupling or back coupling from the motion of the colloids onto the fluid is there? Is it strong, and like, can you use this to start in one flow state, which causes some colloid motion? The colloid motion changes now the flow structure to lead to some new flows.
I can't tell you like the specific details of the model. You might have to ask us too, but I mean, it's good.
I guess I mean in the experiments. Do you see hydrodynamic coupling from the colloid motion to alter the flow field?
So it's very difficult to see flow fields in the system. We have not looked at flow fields of like two interacting swimmers. But we do believe that the interaction between the copper particles, that they interact at a certain distance, that this is largely due to hydrodynamics. But on the other side, like we cannot decouple the chemical field from the hydrodynamic field. So when I tell you like something is due to the hydrodynamics are always due to the chemical field that the particles produce.
I see.
So, if I understand correctly, in the groove experiment, you cannot easily control the persistence of these guys, right? So you cannot tune some parameters of the experiments to make them get stuck for longer or something like that?
I mean, no, we cannot tune the persistence independent of, for example, the swimming speed, which we tune via the fuel.
It would be interesting, I think, to study a situation on the groove with many, many particles and see what's the distribution of cluster sizes if you have something like that. Yeah,
but I mean, this is difficult for these systems because these systems, they don't, like, so if you think about, for example, Cécile Cotin-Bison's gold platinum systems, they swim via a purely redox reaction, so they have a source and a sink. While these particles have only a source, so if you have many particles, they basically inhibit each other because they produce quite a high ionic strength, so the particles would just get stuck. So you can't really use a lot of particles of this type in these experiments.
Yeah, I see.
Okay, one last question.
I'm just curious, on the metal side, do you have any charge also on these particles? I mean, what stabilizes them? Why they don't stick together by van der Waals forces or?
So we don't, so if you measure the zeta potential of platinum particles or of gold particles, then you would usually have surfactants stabilizing the particles. We do not have any surfactants in the system, and I would usually assume that the metal in itself is neutral. So when we look at the zeta potential of just the silica particles, it is roughly minus 35, 38 normally. And then when we cover it with the platinum, it goes to minus 30-ish. So I don't think that the platinum has a positive charge, but it covers some of the negative charges.
So why they don't stick together by van der Waals forces? I mean, usually this is a problem with colloidal particles, they stick together.
So I mean, they would stick if you dry them, but they have an electrostatic double layer around them.
Yeah, but on the metal side, they don't, so I would think there you could have like fairly strong van der Waals interactions.
Yeah, but the systems are always lubricated, so there's always like water
the
layer
flow
between them.
It.
And obviously in the moment, yeah, but we store them just in like Eppendorfs in solutions. So, and they also don't stick. They do stick when you dry them, then
okay.
You can directly see it.
Okay, thank you, Juliane. Let's thank Juliane.